Okay, so let's continue with the second portion of the lecture. So last time we worked with the quadratic over here. So we did this in the part one. We're going to continue with a bunch of other functions. So the next one is trace. You may remember what trace was from the previous lecture. The trace is basically the summation of the diagonal. So it's A11, A22, right? A11 plus A22. So if this is the case, what do you think the trace is if it's just one number, A11? Well, the diagonal of this is just one number. Therefore, it's just equal to A11. So the interesting observation here is that if you have a trace of one dimensional element is equal to the element itself. Okay? So here, trace of a number is just the number itself. Now, what is interesting with the quadratic that we just saw right here, this is quadratic, is that it ends up to be a number. See, if we were to, let's do a quick example. Let's say we have x. Let's say we have 1, 0, 1, 0, 0, 1, 1, 0. So this is x transpose ax. Okay, so this is the quadratic. If we were to multiply by this would be 1, 0. This would be no. This would be 1 and 0. There we go. And then you multiply by 1, 0, which is equal to 1. So the final result of this is just a number. Therefore, the trace of a number is just itself, like what I just showed you, implying that if you take the derivative of the trace of this, it's just equivalent to just taking the derivative of this. Okay? So trace of this expression. Now, of course, this is if x is a vector. There are times when x is not a vector, when you have like x, a, x transpose, right? So that's no longer a number. But for the case when it is just a number, then yeah, you can just take the derivative of this, and we just did this as the quadratic. Okay, so the derivative of the quadratic is the same as the derivative of the trace of the quadratic. Okay? Another interesting property about trace is that trace is rotation invariant, which means that right here, if you were to just move this to the other side, see x transpose, they're actually equivalent. This is a very good example. You should give it a try. Basically, make up some number here and then check that when you rotate them, it's exactly the same. And you can rotate them again. You can put a here again, see? And they're actually equal. Therefore, since they're all equal, then the derivative of the trace of this must equal to the derivative of the rotation, right? After rotation and rotation again. So you can just keep rotating, as well as it's just equal to the derivative of the quadratic, what's inside the trace. Okay? So this is the trace property. Okay, the next one we have is regression. Now, it's easy for people to get confused when there is a summation. Like, how do you take derivative of this? Well, let's look at a simple example where we have w. This is the variable is w. Okay, the variable is not x. So I equals 1 to 2 xi. So this is f of w is equal to this. So if this is the case, this is equal to wx1 plus wx2, right? If you want to take the derivative of this, then it's just x1 plus x2. Okay, so if you take the derivative d dw, you're going to get x1, x2. Notice how this is equivalent to the summation of xi. What this is saying is that you can actually just keep the summation here and just take the derivative. If you just take the derivative, with respect to w, right, then you're just going to get the summation of xi, which is equivalent to if you had tried to sum them up. So this particular example works as well for uh, these kind of things. Yeah. Uh, 1 second. My laptop just froze. Okay, it's better now. Okay, so why don't you take out a piece of paper and give it a try? See if you can take the derivative of this with respect to w. Okay. Okay, so let's continue. Now, with this, we'll do this example together. Essentially, we know that w is the variable, and we can really simplify this expression by letting qi equal to this thing, which is this part. When we do that, we replace it as just qi. Now, we can use the chain rule, which when you take the derivative with respect to q, so df dq. So q is the variable right now. If we take the derivative with respect to q, it will give us the summation I to n qi minus yi. And that's it. This is df dq. Once you have df dq, the chain rule says that then you need dq dw. Okay, so what is dq dw? Well, we learned how to do this previously. This is just a linear. Well, given a linear, it's just xi. Therefore, df dw is equal to df dq times dq dw. Q cancels out, which is equal to the summation of I and qi minus yi xi. Oops. Let me move over here a bit. Xi. So over here is our derivative, and we can replace q back. What was q supposed to be? W transpose xi. So there we have it. Here's the derivative. You can see it's right here. So that's how you would solve a linear regression objective. Now, this requires us to use the chain rule. So make sure you watch the calculus video. Okay, I give everybody the calculus video. If you don't watch the basic calculus video, obviously you're not going to be able to do vector-based calculus, right? You need to know basic calculus so you can do this. Okay, and specifically here we use the chain rule. Okay, the next function we're looking at is called ReLU. The ReLU function looks something like this. Now, if you plug anything below 0, so any negative number, this function will simply give you 0. And if you plug any positive number like 5 here, then this number will give you the exact number back. So 5 will give you 5. So this implies that the slope or the derivative is just 1. Okay, so over here, so basically anything negative, it's going to return a 0, implying that the slope or the derivative here is 0. Anything positive here, all right, it's just going to give you the number back. Now remember, if it goes this way and then it goes up exactly the same, then the slope, the derivative is just equal to 1, because this divided by this is equal to 1. Okay, so ReLU, right? If we just look at ReLU of x. Remember, if this value is negative, the derivative is going to be 0. If this value is positive, then the derivative is going to be 1. Okay? So now we're going to use chain rule again, and we're going to let Q equals to this. So ReLU LU of Q. Well, the derivative of this df dq is equal to 1 if Q is greater than 0. Okay, so this right here is kind of like an indication function. It's an indicator, basically saying that if Q is greater than 0, we're going to get a 1. And if Q is not greater than 0, we're going to get a 0. Okay, that's what this function says. So we now know df dq. We again need to find dq dw. Okay, what was the derivative of this again with respect to w? Well, it's just x. Therefore, x. So you can see that df dw is this expression. Okay, over here I substituted q back in. So that's the derivative of ReLU. Now, ReLU is really important function for modern neural networks. Basically, within neural networks, there are these things called activation functions. And the function they use in today's neural network are all ReLU. So, and therefore, taking the derivative is very, very important with them. Okay, let's move on to the next one, multivariate Gaussian. So it looks something like this, where you have an exponential term of a quadratic. Okay, well, how do we do this? Well, it's not bad. We use the chain rule again, which we take the derivative of this, e to the q, and q is going to equal to minus x transpose ax. Well, the derivative of e to the q is simply e to the q. And from previous quadratic, we learned that the derivative dq dx is equal to a transpose plus a x. Okay, and there's a minus sign, so a minus here. Therefore, the final solution is simply minus a plus a transpose x, which is right here. So the multivariate Gaussian the derivative is also pretty easy. Okay. The next function is called the sigmoid. Sigmoid used to be really important. It's still important today, but the reason is because the original neural networks, they use sigmoid as the activation function. Of course, today, like I told you, it has been replaced by the ReLU function. So if it's being replaced by ReLU, then this one is less important. But we still use it for other purposes. So let's take a look. Well, this is what? Well, it's 1 plus e to the minus x to the negative 1. Okay, so this is equal to this, to the negative 1. Now we can take the derivative. Well, this is just power rule. We move 1 down and subtract this by 1, which would give us 2. And after that, we take the derivative of this, which is e to the minus x times minus 1. Okay, this right here is chain rule. Okay, so I first chain, what did I chain? I first chained this part, and then I chained this part. So in the end, once you have this is the derivative. Now, normally, when you look at the derivative of sigmoid, it's written this way, and they're actually identical. And over here is the derivation. But we don't really need to deal with sigmoid very much. So this is only if you want to know how they're equal. Okay? All right, the next one is the L1 norm. L1 norm. Okay, make sure you watch the video on L1 norm. I'll provide that. So I think I had a video just on norms, and if you know the norms, this will make a lot more sense. But basically, L1 norm is if you put a vector into this, This 1 means L1 norm. So this vector could be maybe 1, -1. For example, L1 norm simply adds up all the absolute of each value. So let's say this is -2. So it will be absolute value of 1 plus absolute value of -2, giving us 3. So that's what an L1 norm is. And once we have the L1 norm, how do we take the derivative? So let's say we look at this very simple example where there are only two elements. Okay. So since that there are only two elements with the L1 norm, we need to know how to take derivative with respect to absolute value. So if you remember back from algebra, absolute value looks like this, right? If you have 1, it's just going to give you 1. But if you have -1, it's going to give you 1 as well. If you have -2, it's going to give you 2. 2 is going to give you 2. So the absolute value function looks like a V. What this tells you is that if the number you put into the absolute value is positive, the derivative is always 1. And if the absolute value you plug in is minus, then the derivative is always -1 because it's going down at the speed of -1. This is going up at the speed of +1. Okay? So if it's just 1 or -1, there's a very special function that represents this, which is called sine. So basically, if it's a positive number you plug into this function, it gives you 1. And then if it's a minus number, it will give you -1. So whatever we just described is literally the sine function as it's defined. Therefore, the derivative is with respect to x1, right, is sine of x, like this. So when you put the vector in here, you simply say, what is the sine of the first one? Well, it's positive, therefore it's 1. Negative, therefore it's -1. Okay? So that right there is the L1 norm derivative. Okay? We're going to pause again and we'll start with the next video later.